This is a demonstration of the DCRYPPS system, developed by Vanderbilt University and Dynamic Object Language Labs, sponsored by the DARPA CASE program. The key functionality of DCRYPPS is to analyze an input cyber-physical systems model and generate attack plans and a set of cyber-physical requirements that will protect the system. We'll use DCRYPPS with two different models, starting with a simple camera model. Here we see the camera model represented in the ADL language. You see the model consists of 4 separate subcomponents. The ADL diagram shows the same information in a graphical form. This is the DCRYPPS browser-based user interface. Here we're going to import the ADL model along with 3 other inputs into the DCRYPPS model representation. Within DCRYPPS, we're able to view and edit the camera control model in a graphical form. Now we select Run DCRYPPS, which begins the analysis of the model, generating attack plans and then generating a set of requirements that will protect the system from attack. Here we see a quick summary of those requirements. And here we see the intermediate attack plan represented as a temporal plan network, a TPN. This attack plan TPN starts on the left side and proceeds to the right. The plan branches at various points, indicating either a choice of multiple alternatives or a split into parallel activities. The labels on each segment of the plan describe the underlying attack activity. Now we see the generated cyber-physical requirements for this model. Clicking on the red C icon shows the applicable information for this requirement that comes from the MITRE KPEC database. Now let's take a look at the requirement that the Jetson component should be absent of any backdoors that an attacker could leverage. First, we look at the KPEC information for this requirement. Clicking on the red arrow icon for this requirement brings us to the graphical view of the model, with the Jetson component being highlighted. Clicking on the R icon in the Jetson component brings us back to the list of requirements in which all of the Jetson-related requirements are highlighted. Now let's download the requirements to preserve this analysis. Now we will use DCRYPPS to analyze another model. This one's much more complex in terms of the number and types of components and their interconnectivity. The system consists of 2 separate aircraft. Here we see a detailed view of the subcomponents and the connections within one of the aircraft. And the ADL diagram shows the model in a graphical form. In DCRYPPS, we import the ADL model along with 3 other inputs. The first is the functional design, which is the JSON representation of the core AADL model. Next, we specify the desirable properties, which identify the mission-critical elements in this model. Next is the class dictionary, which identifies the correspondences between the names of the model components and their semantic meanings. And then finally, we specify the attack access points, which identifies the likely points that the attacker will use to initiate an attack on the system. Once imported, we can view and edit the desirable properties. We can also view and edit the class dictionary of semantic mappings. And here we can view the top-level components of the model. Now when we run DCRYPPS, we can review those same model inputs. Desirable properties and class dictionary, and then specify the target confidence level for the model. A large model like this takes DCRYPPS a few minutes to analyze. We're replaying this part of the video at a higher speed. Just like before, we see the attack plan that DCRYPPS generates, followed by a quick display of the generated cyber-physical requirements. The TPN view of the attack plan is now displayed. This shows all the possible ways that an attacker can compromise the system, starting on the left side, and then picking any of the alternative ways of reaching the right side, compromising the system. Now we view the requirements generated by DCRYPPS for this model. Here we can view the KPIC information for any of the requirements. And then we can look at the graphical display of the top-level components of the model. And again, we can click on the requirement linkage for any component to see all the requirements that are relevant for this assault aircraft. And those are all highlighted in this display. Selecting one of the desirable properties will highlight all the requirements associated with this desirable property. In this case, there's only one, so all the requirements are in fact highlighted. And then finally, we can download the requirements for future use. Now let's use DCRYPPS to analyze a third model. This one is nearly identical to the previous one, except that the system designer has modified some of the critical components to be trusted components, addressing the requirements that DCRYPPS had previously identified. We run DCRYPPS on this model and fast forward through the processing. However, now we see that no requirements have been generated for this trusted model. Also, we see that a probabilistic certificate, a PCC, has been created. The PCC can be used as a certification of the model, so that if additional changes are made to the model, DCRYPPS can simply validate the model against the PCC, assuring the model designer that those changes won't result in any additional requirements being generated. However, if the validation check fails, then a full DCRYPPS analysis should be run again. Thank you for watching this DCRYPPS demonstration. If you have any questions or comments about DCRYPPS, including how it might be applicable to your security analysis needs, please contact us.